Hi, I'm Mark Barsamian with the Ohio University Math Department. Back in Chapter 4, we had been studying metric geometries, and we observed some plane separation behavior that we're used to seeing in drawings. We wondered if our axiomatic geometries that we had been studying up to that point, these metric geometries, if they exhibited analogous kind of plane separation behavior. We consider this desirable plane separation behavior. And we observed that there were some metric geometries that don't have that behavior. So if we wanted to confine our study to axiomatic geometries that did have that desirable plane separation behavior, then we would need to formulate an axiom that describes that desirable plane separation behavior, and then introduce a more restrictive class of axiomatic geometries, those being the metric geometries that also satisfied this additional requirement, satisfied this plane separation axiom. And that's how we came up with the class of geometries that are called Pasch geometries. Those are the metric geometries that satisfy that plane separation axiom. And then in Chapter 5, we introduced angle measure and are now talking about protractor geometries. Well, in Chapter 6, which we start today, we'll start by introducing the notion of triangle congruence. And then we'll observe some familiar behavior of triangle congruence in drawings. And we'll ask the question, do our protractor geometries, our axiomatic geometries that we've been studying, do they exhibit this desirable triangle congruence behavior? And we'll see that there is a protractor geometry that doesn't have that desirable triangle congruence behavior. So if we want to confine our study from now on to axiomatic geometries that do have this desirable triangle congruence behavior, then we'll need to formulate an axiom that describes that desirable behavior. And we'll have to introduce a new class of axiomatic geometries that will be the protractor geometries that also satisfy this additional requirement. They satisfy this axiom about triangle congruence. And so that's how we'll arrive at what will be called neutral geometry. Neutral geometries will be those geometries that are protractor geometries that also satisfy this additional requirement, this triangle congruence axiom. This video is produced for Ohio University Math 3110-5110, College Geometry. The reading for this video is from section 6.1, the SideAngleSide Axiom, more specifically page 124 to the top of page 128, in the book Geometry, A Metric Approach with Models by Millman Parker. The homework is this short collection of 4 exercises from section 6.1 of the book. So as I said, we'll start with the definition of triangle congruence. We'll observe some desirable triangle congruence behavior that we see in drawings, and then we'll formulate what are called the triangle congruence axioms, and then introduce neutral geometry, and then we'll have our first proofs about congruences in neutral geometry. So let's start with the definition of triangle congruence. When comparing drawn triangles, one of the things that we can do is slide one drawn triangle on top of another one and see if they fit. When they do fit, all the sides are the same size and all the angles are the same size. That is, all the corresponding parts are the same size. We want to have an analogous notion of being able to compare triangles in axiomatic geometry. That's the idea of triangle congruence. In order to formulate a definition of triangle congruence in axiomatic geometry, it helps to have a notion of corresponding parts of triangles. So we'll do that in the following way. Let ABC and DEF be 2 triangles in a protractor geometry, and let F be a function whose domain is the set of vertices from triangle ABC, that is just this set of 3 letters, and whose range is the set of vertices of triangle DEF, that is that set of 3 letters. And let F be a bijection. That means it's injective and it's surjective. Well, then associated to the bijection F is an automatic correspondence of 6 pairs of parts of the 2 triangles. So for instance, segment AB of that green triangle ABC corresponds to segment f of A, f of B of triangle DEF. So in other words, if you take vertex A and you feed it into this function f, what comes out is a vertex f of A. It's one of these three letters. And if you feed in vertex B into that same function f, what comes out is a vertex f of B in this other triangle. And those two vertices define a side of that red triangle. That is this side, f of A, f of B, with a bar over it. So that side of triangle DEF corresponds to this side of triangle ABC. And so forth for the remaining sides of the green triangle and the remaining angles of the green triangle that correspond to sides and angles of the red triangle. Now I'll introduce the definition of congruence between two triangles. The words a congruence between triangle ABC and DEF we can use when those are triangles in a protractor geometry. So remember that triangles exist in metric geometries. In metric geometries we have the notion of line segments, and triangles are defined to be unions of line segments. So triangles actually exist in metric geometries. And remember that angles also exist in metric geometries. But it's not until we get to protractor geometries that we have the notion of the measure of an angle. So we're going to use the term congruence of triangles only in protractor geometries. Now, what those words mean, a congruence between those two triangles, is the following. They mean a bijection, that is a function f, from the set of vertices of that green triangle to the set of vertices of that red triangle, and a bijection that has this additional property. Each pair of corresponding parts is congruent. That is, for instance, that segment of that green triangle is congruent to the corresponding segment of the red triangle. And that angle of the green triangle is congruent to the corresponding angle of the right triangle. So notice that this is 6 pairs of parts that are congruent. Now the definition of congruent triangles. We say that triangle ABC and DEF are congruent when those are triangles in a protractor geometry and in this situation where there exists a congruence between those triangles. So in other words, when there exists a function f from the vertices of triangle ABC to the vertices of triangle DEF such that each pair of corresponding parts is congruent. Now notice that the definition of congruent triangles does not have a symbol in it besides just the symbol for those triangles. There is a symbol to indicate a particular congruence. That's this. That congruent symbol means the following. It means that this particular bijection, f, that's defined this way, f of A is D, f of B is E, and f of C is f. That's a particular function. So this symbol means that that particular function is a congruence. Now there's some subtlety in this congruent symbol. Observe that if this symbol is true, then triangle ABC and triangle DEF are congruent, but that symbol means more than just the sentence triangle ABC and triangle DEF are congruent. It means that this particular bijection is a congruence. That is, it's possible for triangle ABC and DEF to be congruent and yet have this symbol, that is this congruent symbol, has a slash through it. So for example, consider these two triangles, ABC and DEF. The statement triangle ABC is congruent to triangle DEF is true. Why? Well, here's a function, the function that takes these points in this order and spits out these points in that order. That's a congruence. The function f sends that vertex A to that vertex D. It sends that vertex B to that vertex E, and it sends that vertex C to that vertex F, notice that the corresponding parts are all congruent. This side is the same length as its corresponding side. This angle is the same measure as its corresponding angle, and so forth. Now, this symbol here is true. Triangle ABC congruence symbol, triangle DEF, is true. And the reason is that same function is a congruence. That function that sends vertex A to vertex D, sends vertex B to vertex E, and sends vertex C to vertex F. And that's what this congruence symbol is saying. Now, consider this. This statement is true. Triangle ABC is congruent to triangle DFE. Notice we've changed the ordering. Here we said triangle DEF. Now we're saying triangle DFE. We changed the ordering in that triangle. We didn't change the ordering in the letters of this triangle. But we can still say that those triangles are congruent. Why? Well, we can still use that same function as a congruence. The function f that sends vertex A to vertex D, that sends vertex B to vertex E, and sends vertex C to vertex F. That's the same exact congruence that was used in those two previous sentences. So that function still works as a congruence. Now, since there exists a congruence from the vertices of that triangle to the vertices of that triangle, we say that those triangles are congruent. It happens that the bijection uses the vertices listed in a different order, but that's okay. To say that the triangles are congruent just means that there is a bijection, some bijection. But notice that this statement, triangle ABC congruence symbol, triangle DFE, that's false. Because that symbol put in between those symbols is about this function. And that function is not a congruence. So that function sends vertex A of the left triangle to vertex D. So vertex A goes to vertex D. It sends vertex B to vertex F. And it sends vertex C to vertex E. Well, notice that the measure of angle ABC is 30. The green angle is 30 in that left triangle. And the corresponding angle in the right triangle is triangle DFE, that green angle. And notice that that green angle has measure 90, not 60. So those corresponding parts are not congruent, and so even though those triangles are congruent, this symbol is false. So that's the subtlety in that congruence symbol that I mentioned on the previous page. Subtlety in the congruence symbol. Now for our next example, we'll discuss verifying a congruence. I won't actually do the exercise. It's one of your homework exercises, 6.1, number 2. You're given 4 points in the upper half plane, A, B, C, and D. And you're asked to prove that for Poincare triangles, ABD and CBD, those are Poincare triangles, that the following is true. Triangle ABD, congruence symbol, triangle CBD. Now you're supposed to confirm that that's true. Well, that means that you're supposed to use the bijection of vertices that sends A to C and sends B to B and sends D to D, and then show that each pair of corresponding parts is congruent. Well, that will involve verifying that each of these 6 pairs of corresponding parts is congruent. That's going to be tedious. Notice again, those are Poincare segments and Poincare angles. And there are 6 congruences to check. Now observe that triangle congruence is an equivalence relation. There's a typo here. You'll prove that in a homework exercise. That's exercise 6.1, number 1. In a protractor geometry, congruence is an equivalence relation on the set of all triangles. Now remember the proof structure that'll be required. You'll need to prove that congruence is reflexive using the following kind of proof structure. To prove that congruence is reflexive, you'll suppose that a triangle is given, and you'll somehow show that the triangle is congruent to itself. Now, what does that mean, though? Well, to show that the triangle is congruent to itself involves showing that the requirements of the definition of triangle congruence are satisfied. That is, you'll have to provide an example of a bijection from the vertices of triangle ABC to the vertices of triangle ABC. You'll have to come up with some example of a bijection and show that it works, that it is a congruence, because that's the definition of the sentence that this triangle is congruent to itself. And you'll have to prove that congruence is symmetric, and you'll have to use the following kind of proof structure that we've always used to prove that some relation is symmetric. You'll have to suppose that triangle ABC is congruent to DEF, and then somehow show that therefore triangle DEF is congruent to triangle ABC. Now, again, realize what that's going to entail. To show that triangle DEF is congruent to triangle ABC will involve showing that the requirements of the definition of triangle congruence are satisfied. That is, you're going to have to come up with an example of a bijection from the vertices of triangle DEF to the vertices of triangle ABC and show that that bijection is a congruence. Now here's a hint for that. In order to come up with a bijection G that works, you'll need to use the given fact that triangle ABC is known to be congruent to triangle DEF. That's from that first step. That's the given. Now that's a defined statement. You'll need to unpack that defined statement and follow it with a statement that expresses what it really means. Now that unpacked statement will involve the existence of a bijection, F, that is known to be a congruence. Now the hint is, use that known bijection F that you know is a congruence in some way to define the bijection G that you need. And finally, you'll need to prove that congruence is transitive using the following kind of proof structure. Suppose that triangle ABC is congruent to DEF and that triangle DEF is congruent to GHI, and then some steps, and somehow show that therefore triangle ABC is congruent to triangle GHI. Now I'd like to talk about desirable congruence behavior. When comparing drawn triangles, we know that if enough parts of one drawing fit on top of the corresponding parts of another drawing, then all the other parts will fit as well. This can be said more precisely. To determine whether or not two drawn triangles fit on top of each other perfectly, you would have to officially need to verify that every pair of corresponding drawn line segments fit on top of each other, and also that every pair of corresponding drawn angles fit on top of each other. That's a total of 6 fits that would need to be checked. But we know that with drawings, you don't really need to check all 6 fits. Certain combinations of 3 fits are enough. Here are 4 examples of sets of 3 fits that will guarantee that 2 drawn triangles will fit perfectly on top of each other. The first one is this. If 2 sides and the included angle of the first drawn triangle, so these 2 sides in this drawn angle, if those fit perfectly on top of the corresponding parts of the second triangle, then all the other parts will fit as well. The third side will fit perfectly, and the other 2 angles will fit perfectly as well. Here's another set of 3 fits that will guarantee that 2 drawn triangles will fit perfectly. If 2 angles in the included side of the first triangle, so 2 angles in the included side, if those fit on top of the corresponding parts of the second triangle, then all the other parts will fit as well. Here's a third set of 3 things that we can check. If all 3 sides of the first drawn triangle, this side, and this side, if all 3 of those sides fit perfectly on top of the corresponding parts of the second triangle, then all the remaining parts always fit as well. And finally, if two angles and some non-included side, so this configuration, these two angles in this side that's not the side between them, if those fit perfectly on top of the corresponding parts of the second triangle, then all the remaining parts fit as well. Well, we would like our axiomatic geometry, line segment congruence and angle congruence and triangle congruence, to have this same sort of behavior. We could refer to this as desirable triangle congruence behavior. That is, this is behavior that we just are used to seeing happen in drawings. But we can articulate in words desirable triangle congruence behavior for our axiomatic geometry, which is a geometry of words. So all of those behaviors are described here in words. If two sides of the included angle of the first triangle are congruent to the corresponding parts of the second triangle, it should be true that all the remaining corresponding parts are congruent as well. So that would mean that the triangles would be congruent. And so forth for those other three kinds of desirable behavior that we notice that happen in drawings and that we would like to have happen in our axiomatic geometry as well. So those three sentences describe those three other kinds of behavior. Well, an obvious question is, does every protractor geometry have the desirable congruence behavior? Well, let's consider this example. In the taxicab plane, let triangle ABC be these 3 points, -1, 1, 0, 0, and 1, 1. So this green triangle. Let triangle DEF be made up of these 3 points, 2, 2, 2, 0, and 4, 0. Observe that segment AB is congruent to segment DE. Segment AB is this segment. That segment is 2 units long in the taxicab plane because, remember, the way you measure distance in the taxicab plane, to get from A to B, you go down 2 and over 2, and that's why the length of that segment is 2. In this triangle, the length of segment DE is also 2, because to get from D to E, you just go down 2. In the left triangle, the measure of angle ABC is 90. That's a right angle. Remember that the angle measure for the taxicab plane is the same as the Euclidean angle measure. In the triangle that's the red triangle, angle DEF is a 90-degree angle as well. And finally, segment BC in the left triangle is 2 units long, and segment EF in the red triangle is also 2 units long. So we have 2 triangles that have a configuration such that 2 sides and the included angle are congruent to the corresponding parts of the second triangle. But notice in these 2 triangles, the third sides are not congruent. Side AC is 2 units long. Side DF is 4 units long. So side CA is not congruent to side FD. So this example shows that the taxicab plane does not have the desirable triangle congruence behavior. Well, that answers our question. Our question was, does every protractor geometry have that desirable triangle congruence behavior? And the answer is no, because we've seen an example of a protractor geometry that does not. Well, we would like to focus from now on protractor geometries that do have the desirable triangle congruence behavior. But we see that if we want to have that behavior in a protractor geometry, we're going to have to require it by specifying that behavior in some additional axioms. So here are some axioms that describe that desirable triangle congruence behavior. The SideAngleSide Axiom is this. We say that a protractor geometry satisfies the SideAngleSide axiom to mean this. If there's a bijection between the vertices of 2 triangles and 2 sides in the included angle of the first triangle are congruent to the corresponding parts of the second triangle, then all the remaining corresponding parts are congruent as well. So the bijection is a congruence, and the triangles are congruent. So that's a description in words, an axiom that expresses in words that first type of desirable triangle congruence behavior. Then we define the angle-side-angle axiom to articulate that second kind of desirable triangle congruence behavior. We define the side-side-side axiom to describe that third type of desirable triangle congruence behavior. And finally, we define the angle-angle-side axiom, AAS, to articulate that fourth kind of desirable triangle congruence behavior. Now, you might think that it would be necessary to add all four axioms as requirements to guarantee that those four kinds of desirable congruence behavior will all also be observed in axiomatic triangles. But the amazing thing is that we don't need to require all four axioms to be satisfied. We can require just one axiom about just one kind of desirable behavior. We can just require that that one axiom be satisfied. And then we can prove theorems to show that triangles will also have the other three kinds of desirable behavior. That's the idea behind the definition of what's called neutral geometry. So here's the definition of neutral geometry. A neutral geometry, or absolute geometry, is a protractor geometry that also satisfies the side-angle-side axiom. In Chapter 6, we'll prove three theorems about desirable triangle congruence behavior. One theorem will be this: every neutral geometry satisfies angle-side-angle. So remember, a neutral geometry is a protractor geometry that satisfies side-angle-side. So this theorem says basically, if you have a protractor geometry that satisfies side-angle-side, then it will also satisfy angle-side-angle. We'll prove a theorem that says every neutral geometry also satisfies side-side-side. And finally, every neutral geometry also satisfies angle-angle-side. Now note that the statements of those three theorems have been mentioned here just as an introduction to the coming material. Those three theorems have not yet been proven, and they don't yet have theorem numbers, so we may not use them in any of our proofs yet. Soon, but not yet. Now I want to have a brief digression about names of theorems. Names of theorems often follow an informal convention. They're named for the situation described in their hypotheses. For example, suppose two theorems are stated as follows. Theorem 1 says, if the dog is blue, then the car is red. Theorem 2 says, if the car is red, then the bear is hungry. Following the naming convention, Theorem 1 would be called the blue dog theorem because the hypothesis of that theorem is involving the blue dog. Theorem 2 would be called the red car theorem because its hypothesis says the car is red. It's important to realize that the red car theorem could never be used to prove that a car is red. The red car theorem tells us something about the situation in which we already know that the car is red. That theorem tells us that in that situation, the bear is hungry. The red car theorem says if the car is red, then the bear is hungry. So we use this theorem, the red car theorem, in the situation where we already know the car is red. If we do not know that the car is red and we want to prove that the car is red, then we'll need a theorem that has the statement the car is red as part of the conclusion. We see that the blue dog theorem would work. Let's go up and look at that. The blue dog theorem says if the dog is blue, then the car is red. That's the theorem that can be used to prove that the car is red. So one strategy for proving that the car is red would be the following. First, prove somehow that the dog is blue. Then use the blue dog theorem to prove that the car is red. This might sound wacky, all of this discussion about blue dogs and red cars and hungry bears, but it has a direct bearing on the use of the side-angle-side axiom. The axiom is named for the situation in the hypothesis of the axiom. Let's go up and look at that. The side-angle-side axiom says, if we have this configuration of objects and two sides in the included angle of the first triangle are congruent to the corresponding parts of the second triangle, that is, if we have congruent side angle sides, then something else. So we use this axiom in this situation where we already know that we have congruent side angle side. So the SideAngleSide axiom could never be used to prove that two triangles have congruent corresponding side angle side. No, the SideAngleSide axiom tells us about the situation in which we already know that two triangles have those corresponding parts congruent. The axiom tells us that in that situation, the triangles are congruent. And finally, we'll have our first proofs about congruences in neutral geometry. We'll consider two examples of this form. In neutral geometry, given some configuration of objects with some congruent objects, prove that some other objects are congruent. Now, at the current time, our only available tool for proving that anything is congruent is the SideAngleSide axiom. Now, since that's our only tool available, our only possible approach is the following. We have to have a proof structure like this. We start with saying, in neutral geometry, given some configuration of objects with some congruent objects, that's that given stuff. And we're going to end by saying that the other objects are congruent. But what's going to have to go in the middle? Well, we're going to have to do this stuff in the middle. We're going to have to identify two triangles whose parts include those other objects that we need to prove congruent, and triangles that are known or can be shown to have congruent side angle sides, and then use the SideAngleSide axiom to justify saying that those two triangles are congruent, which means that all their corresponding parts are congruent. And that's how we would then end the proof, because therefore we would have shown that some other parts were congruent that we needed to show. So again, note the proof structure. We have to get from this green statement about a known configuration of objects with some congruent objects, and we need to get to a statement about some other objects that are congruent, and the only way to get there currently is to use the SideAngleSide axiom somehow. Here's our first example. In neutral geometry, given quadrilateral ABCD such that AB is congruent to AD and such that ray AC is the bisector of angle BAD, given all that stuff, prove that angle ABC is congruent to angle ADC. So an illustration of that would be the following. Now there are two possible illustrations. One is this one. Here's a configuration of objects, quadrilateral ABCD, such that AB is congruent to AD, and ray AC is the bisector of angle BAD. We're supposed to prove that these two angles are congruent. But notice that in the statement of the problem, it does not say that the quadrilateral ABCD is convex. So it could be that it's a non-convex quadrilateral. So we could have this configuration. That quadrilateral could be non-convex. Now I see that I've forgotten to mark some given stuff. Segment AB is known to be congruent to segment AD, and ray AC is known to be the bisector of angle BAD. So another illustration of the statement of the thing we're supposed to prove is, given all this stuff, prove that these angles are congruent. Well, here's the proof following that structure. We start with suppose all that given stuff is true. Now we have two possible configurations, either that configuration for the given stuff or that configuration for the given stuff. And let's look ahead to see how this proof is going to end. Notice the end of the proof is we have proven that those two angles, angle B and angle D, are congruent, or in this configuration of a non-convex triangle. So there is that proof structure. That we know how that proof has to begin and how it's going to have to end. But how do we get there? Well, let's look at step 2. Step 2 is to note that C is in the interior of angle BAD, and that CAB is congruent to CAD. That's this drawing or this drawing for those two possible configurations. And that's just by the definition of angle bisector. Also note that side AC is congruent to itself. That's just by the reflexivity of segment congruence, or more simply, the segment's congruent to itself because it has the same length as itself. Now, how do we convey that in a drawing? Well, we just draw segment AC and we just put mark on it. Now, there are two different ways that that segment could look, depending on whether we're looking at the green drawing or the red drawing. Statement 4 says, triangle CAB is congruent to triangle CAD. Why? Well, by the SideAngleSide Axiom. Remember, that's our only tool so far for proving that anything is congruent. So here's the illustration. I convey that those two triangles are congruent by shading them and putting a congruence symbol inside them. And also notice that I show the parts that were involved in that. I show the marks showing that the congruent sides were there, the congruent angles, and that third congruent side. So those are the parts that were involved in setting up the use of the SideAngleSide Axiom. And in the other drawing, it would look like this. There are the shaded regions with the congruence marks indicating those two triangles that are congruent. And also, there are the marked objects that were the congruent side angle sides that enable us to use that axiom. Now, the final statement is here now. We get to just say that those angles are congruent. Why? Well, it's because these triangles are congruent, so all their corresponding parts are congruent. That is, the definition of triangle congruence is that all the corresponding parts are congruent. So that's the end of that proof. And notice again, it follows that structure. We have some given configuration of objects with some known to be congruent, and we have a goal to prove some other objects are congruent. To get there, we have to identify some triangles that can be shown to be congruent using the SideAngleSide Axiom. Our last example for the video will be quite hard. Prove the following. In neutral geometry, if the diagonals of a quadrilateral bisect each other, then the opposite angles of the quadrilateral are congruent. So that would be illustrated in the following way. Here's an illustration of a quadrilateral where the diagonals bisect each other, and here's a drawing showing that the opposite angles of the quadrilateral are congruent. Now remember what it means to bisect. To say that the green diagonal bisects the red diagonal means that it splits the red diagonal up into two congruent pieces. To say that the red diagonal bisects the green diagonal means that it splits the green diagonal up into two congruent pieces. Now notice, these two pieces are congruent to each other. They're not necessarily congruent to these red pieces. These two red pieces are congruent to each other. It looks like the red pieces are both longer than the green pieces. And again, we're supposed to prove that these opposite pairs of angles are congruent. This pair of angles is congruent, and this pair of angles is congruent. Well, so here's the proof. We start by saying, suppose all that stuff is given. So there's our drawing again, the drawing of the configuration mentioned in the hypothesis. And let's skip ahead to the very end of the proof. Notice that we show in the very end of the proof that this pair of opposite angles are congruent and this pair of opposite angles is congruent. So that's the very end, and you can see it's many steps in the future. Now, how do we get there? How do we get from where we are at the beginning to where we need to go? Well, first of all, the proof will be divided into parts. First part, we're going to show that one pair of opposite angles is congruent. Now, remember, the strategy is going to be to identify some triangles that we can prove are congruent using our only available tool, SideAngleSide. And then that will be what we need in order to prove that those angles are congruent. So here we go. We have this given configuration, a given quadrilateral whose diagonals bisect each other. Step 3, we can label the vertices of this quadrilateral however we want. So let's label them this way. The lower left vertex in this picture is A, and then B, C, D, and we'll label that midpoint M. The midpoint of that point where those diagonals intersect is a midpoint for each of those diagonals. Well, remember, we're trying to prove that some triangles are congruent somehow. Got to identify the triangles, and the only tool that we have that will allow us to prove that triangles are congruent involves side angle side. So we're going to have to find some angles that we know are congruent. So far, we just know something about some segments that are congruent. So we're going to need some angles in order to use the side angle side axiom. Well, look, statement 4 says that angle AMB is congruent to angle CMD by the vertical angle theorem. That's theorem 5.3.9. And then statement 5 says triangle AMB is congruent to triangle CMD. Now remember, our only tool for showing anything is congruent is the side angle side axiom, so that's going to be what we have to use. And sure enough, that's the justification. Now, you can't just say by the side angle side axiom. You really need to hit the reader over the head and say, how did you use the side angle side? In other words, list the things that you know are congruent. So we're using the fact that AM is congruent to CM, that's that pair of green segments, and BM is congruent to DM, that's this pair of green segments, and the included angle, angle AMB, is congruent to CMD, that's marked there. So notice the drawing shows the two triangles that we're claiming are congruent, highlights them by shading them and putting a little congruent symbol in them, and also shows the parts that were involved in being able to say that those triangles are congruent. But notice that the drawing leaves out some other stuff. So for instance, I don't draw side BC. I don't draw side AD of that quadrilateral because they're not mentioned in this statement. This statement is just about those triangles. So the way to be clearest, so that your reader will really focus on the things you need them to focus on, the way to be clearest is to leave out all the other stuff. Notice in the previous drawing, the previous statement was just about congruence of two angles using the vertical angle theorem. I left out all the other stuff that's not necessary. I didn't show the sides of that quadrilateral. I just showed the things that were involved in this statement. Okay, so we've proven that these two triangles are congruent. Well, that allows us to say that these two angles are congruent. Why? Well, that's because we know that these triangles are congruent from the previous step, so therefore, by the definition of triangle congruence, all their corresponding parts are congruent. Now, we can also say that angle CAB is congruent to angle ACD. That's the same angles, just that I've zoomed out. Instead of using an angle that involves ray CM, I'm using an angle that involves ray CA. And that's okay because ray CM is the same ray as ray CA. Let's go on. Now let's show that angle CAD is congruent to angle ACB. Well, we're going to do the same sort of thing that we did in the few preceding steps. We're going to prove that a different pair of angles is congruent using the vertical angle theorem, and prove that a different pair of triangles is congruent, again, using the side angle side axiom. And that will allow us to say that a different pair of angles is congruent by the definition of triangle congruence. And again, we'll zoom out and state that same result about angles in a slightly different way. Now finally, we need to show that angle BAD is congruent to angle DCB. So that's one of the pairs of angles, opposite angles on the quadrilateral that we're hoping to prove congruent. So here we go. Now we're going to need two facts. One is that C is in the interior of angle BAD. That's this configuration. Why do we know that? Well, by theorem 4.5.4, we know that a quadrilateral is convex if and only if each, this should say each vertex, each vertex is contained in the interior of the opposite angle. So that allows us to say that C is in the interior of that angle and A is in the interior of that angle. Why do we need that? Well, because we're going to use what's called the congruent angle addition theorem. Observe that this angle is congruent to this angle, and this angle is congruent to that angle. And so by the congruent angle addition theorem, we know that the larger angle, BAD, is congruent to this larger angle, DCB. So there we've done it. We've proven one pair of opposite angles from that original quadrilateral is congruent. Now proof part 2 is to generalize to the other pair of opposite angles. Now we can do this without doing any additional work besides just explaining clearly. So notice that in part 1 we showed that one pair of opposite angles is congruent. Now to do that, we chose the letters A, B, C, D for the vertices of the quadrilateral. So we put the A, B, C, D there, and we typed up all those steps, and we ended up showing that this angle A is congruent to this angle C. The key thing is that we chose those letters for the vertices. Well, that quadrilateral shape was there. It didn't have vertices named in the beginning. We could have assigned the letters differently. We could have assigned them this way. Same quadrilateral, but just put the letters on differently. Keep all those steps in part 1, the same typed up steps with all those letters. All those statements are still true. The drawings would look different, but that's all right. The statements are the key thing. And the result would be that we would have shown that angle A is congruent to angle C. But in the original quadrilateral, those angles would now be the other pair of opposite angles. So the result is that we've shown that both pairs of opposite angles are congruent. This pair of opposite angles is congruent to each other, and this pair of opposite angles is congruent to each other. Well, that's the end of that example, and that's the end of the video. Thank you.